Good day, class. In this video, I will teach you the complete steps of the Denavit-Hartenberg notation and how to construct and fill out a D-H parametric table. So there are 4 steps in the Denavit-Hartenberg notation. Step 1 is to assign the frames according to the 4 D-H frame rules, which we already have done before the lecture of the rotation matrix, position vector, and homogeneous transformation matrix. Then step 2 is to fill out the D-H parametric table. Okay? Or, sorry, to construct and fill out the D-H parametric table. So, D-H parametric table is the shortcut of obtaining what we call the homogeneous transformation matrix. So this is the short method. The long method is to derive first the rotation matrices and the position vectors, then concatenate them inside or concatenate them to have a 4x4 homogeneous transformation matrix. While in the short method, we will use this kind of table to obtain the homogeneous transformation matrix. Okay, so this is the main function or main feature of the Denavit-Hartenberg notation to obtain fast the homogeneous transformation matrix. Okay, but be reminded or note that before studying the construction and filling out of the D-H parametric table, you need to study and fully understand first what is rotation matrix, position vector, and the parts of the homogeneous transformation matrix. Okay, and because we already studied the rotation matrix and position vector as well as the homogeneous transformation matrix, we are ready to construct and fill out a D-H parametric table. Then step 3 is to plug the table into the homogeneous transformation matrix form. So after filling out this table, we will convert the table into homogeneous transformation matrix using this standard formula of the homogeneous transformation matrix. So this formula came from the derivation also of the rotation matrix and the position vector. Then after obtaining or plugging the table or the conversion of the parametric table into homogeneous transformation matrix, we will now multiply the matrices together to obtain the homogeneous transformation matrix of a mechanical manipulator. Okay, so let's start with the Denavit-Hartenberg table. So this is an example of a Denavit-Hartenberg table. So this table is from a Cartesian manipulator. Okay, a 3 degrees of freedom Cartesian manipulator. It consists of columns and rows. The columns are the parameters. Okay, it is where the parameters are located. The 4 parameters are theta, alpha, r, and d. while n is not a parameter. N is just a description. Okay? N is just a description of the number of frames for each row. Okay? So, rows is equals to the number of frames minus 1. So, for this table came from a Cartesian manipulator. This Cartesian manipulator with a stand have 5 frames from the base to the end effector. So from the base we have as frame 0, then up to the end effector we have frame 4. So if we create the homogeneous transformation matrix equation for this mechanical manipulator, we will have this. So H04, just like from the rotation matrix. Okay, they have the same rules in creating their equation. So H04, then H04 will come from H01 times H12 times H23 times H34. Okay, so this is the equation for this mechanical manipulator. Okay, so we have 5 frames. So the number of rows for this mechanical manipulator is 4. Sorry, is 4 because number of frames is equals to 5 minus 1, so it is 4. Then each row represents the homogeneous transformation matrix of the reference frame up to the projected frame. So this frame up here represents the homogeneous transformation matrix from 0 to 1. Okay? The homogeneous transformation matrix of frame 1 relative to frame 0. So this is how you read this. The proper way to read this is the homogeneous transformation matrix of frame 1 reference or related to frame 0. Okay? Reference to frame 0 or related to frame 0. Next. So this second row represents the homogeneous transformation matrix of frame 2 reference to frame 1. Then this row 3 represents the homogeneous transformation matrix of frame 3 reference to frame 2. And this last row represents the homogeneous transformation matrix of frame 4 reference to frame 3. Okay. So these are the rows. Okay, so remember that. So in this class, the arrangement of our parameters starts with theta, then alpha, then R, then D. So what are these? What are these 4 parameters? So we are calling it D-H Parametric Table. So the theta and alpha are the rotation parameters. Okay, remember that. Theta and alpha are the rotation or orientation parameters, while D and R are the position or translation parameters. Okay. So the units of the rotation orientation parameters are region or degrees, Then the position or translation parameters is a unit of length or the units of length. So it can be centimeters, millimeters, inches, or foot. Okay. So this is arranged like this in our table: theta, alpha, r, and d. Okay. So I will explain what does theta and alpha means, as well as d and r. Okay. So theta is the rotation around Zn minus 1 that it is required to get x sub n minus 1 to match x sub n. With the joint variable theta if joint is revolute or twisting joint. Okay. So for example, we have here two frames. The frame n and frame n minus 1. So n means an integer that starts with 1. Okay. So if n is equals to 1, then n minus 1 is equals to 0. Okay. So theta is the rotation around Zn minus 1. So this is a Zn minus 1. And the rotation here is what we call theta. Okay. Theta is the rotation that is required to get x sub n minus 1. This is x sub n minus 1 to match with the direction of the x sub n. Okay. So in these positions, x sub n minus 1 have the same direction with x sub n. So the theta here is equals to 0 degrees. So we will use degrees as the unit of our theta and alpha. Okay. So this is our first example in this directions. Okay. So example 2, if our x sub n minus 1 pointed to the left, so our y sub n minus 1 will change direction according to the D-H frame rules. So it will be pointing out forward. It will point forward. Okay. So x sub n minus 1 is now pointing to the left, while x sub n is still pointing to the right. Okay, so the theta here, is we need theta, we need a value of theta that will make x sub n minus 1 to have the same position with x sub n. Okay. So x sub n minus 1 is pointing to the left and x sub n is pointing to the right. So if we rotate at Zn minus 1, we need 180 degrees. Okay, we need 180 degrees to make x sub n minus 1 point to the same direction of x sub n. So our theta here is 180 degrees. Okay. Example 3. Let's say we have here theta 1. Okay. Because example, this is a revolute joint. Okay, this is a revolute joint. And this frame N is also located in a revolute joint. Okay, so it says here that if there is a joint variable theta, if it's a revolute or twisting, uh, you will add the theta to the theta. Yes, you will add the theta. Or you will add theta 1 to the theta. Okay, to the angle that is required to match the direction of x sub n minus 1 to x sub n. So for example, let's rotate x sub n minus 1. I will put x sub n minus 1 backward. Then, so because x sub n minus 1 is now pointing at the back, y sub n minus 1 will also change direction. It's now pointing to the left. Okay. So, theta is the required angle to match the direction of x sub n minus 1 to the direction of x sub n. So, we are rotating counterclockwise. So, the value of theta to match x sub n minus 1 to x sub n is 270 degrees. Okay, this is 270 degrees. Okay, from the back up to the right. Okay, we are rotating counterclockwise. So this is a positive direction. So this will be 270 degrees plus the given joint variable theta 1. Okay. So joint variable theta 1 is different to parameter theta. Okay. Joint variable theta 1 is given if the joint is a joint variable or a twisting, sorry, if the joint is a revolute or a twisting joint. Okay, so this is theta. Next is alpha. So alpha is also a rotation parameter. So it is the rotation around x sub n. So this is x sub n that is required to match Zn minus 1. Zn minus 1. Wait. To match Zn minus 1 to Z sub n. Now the axis of rotation is Z sub, the axis of rotation is x sub n. Okay. The axis of the rotation now is the x sub n. So the rotation along x sub n is the alpha. Okay. This is alpha. Again, we are rotating counterclockwise to have a positive rotation angle. Okay, so for example, this is our frame n minus 1 and this is frame n. We want to match the direction of z sub n minus 1 to z sub n. So what will happen here, okay, if we say zn minus 1 must match with z sub n, what it means is that it should be look like this. Should be look like this. It will rotate here. There will be a rotation here. Yes. Then the frame n minus 1 will go here. Then Zn minus 1 will change its its orientation and direction. Okay. So Zn minus 1 will become like this. So again, the rotation happens at the axis of x sub n. So it's like from here it rotates to there. Okay. So now Zn minus 1 has the same direction with Z sub n. So the amount of rotation is 180 degrees. Okay. Again, we are rotating counterclockwise. So this is positive 180 degrees. Okay. So that is alpha. Okay. So what I'm showing to you is not what it is not the actual that you will do while obtaining the parameters of theta and alpha. So you will just imagine this. Okay? You will just imagine these rotations, the rotations of theta and rotations of alpha. So if you are rotating to obtain alpha, there is a technique faster than this. Okay? There is a technique faster than this. So the technique is to imagine that x sub n, okay, that x sub n, sorry, so x sub n x sub n, z sub n, z sub n, and zn minus 1 is at the same zn minus 1 is at the same origin. Okay, this 3. So imagine they are at the same origin. It's fine if zn minus 1 and z sub n is at the opposite direction. Okay. So imagine that they are on the same origin. Then perform the rotation alpha. Okay, counterclockwise. Okay. Then try to imagine if Zn minus 1 will rotate counterclockwise up to the direction of Z sub n. So that the amount of the rotation is 180 degrees. Positive 180 degrees because we are rotating counterclockwise. Okay. So another example, if we are, okay, let me take this one. This example of theta. Okay. I will use again this as my frame n. Okay. This is my frame n. This is my frame n minus 1. So I will remove theta. It will not be confusing. Oh, Zn minus 1 is the same direction with Z sub n. So let me change the direction of Zn minus 1. Let's say the direction of Zn minus 1 is to the right. So x sub n minus 1 to the front. Then y sub n minus 1 based on the right hand rule will now point upward. Okay, so this will now be the frame n minus 1. Okay. So we have frame n, then frame n minus 1. Get the alpha. Get rotation alpha. Okay. So rotation alpha perform the rotation alpha. So the technique here is to imagine that, oh sorry, you can't have x sub n minus 1 parallel to x sub n. So I will point x sub n minus 1 to the back. Sorry. So this will be x of n minus 1. Then this is j sub n minus 1. Okay, sorry. Again. This is jn minus 1. Then according to the right hand rule, y minus 1, y sub n minus 1 will point downward. Okay. So this is frame n minus 1. It should follow the D-H frame rules. Okay. So Jn minus 1 is pointing to the back. J sub n is pointing upward. Okay. So imagine that x sub n, j sub n, and j sub n minus 1 is at the same origin. Okay. So Jn minus 1 is perpendicular with J sub n. Again. So let's perform the rotation alpha. Okay. Let's perform the rotation alpha. Oops, sorry. Yeah. Okay. So again, this is counterclockwise. So we need to match j sub n minus 1 to j sub n. So to match j sub n minus 1, we perform the rotation alpha. So we will rotate from here up to there. So this is just 90 degrees. Okay, this is just 90 degrees. So again, j sub n and j sub n minus 1 is perpendicular with each other. If we rotate at x sub n and j sub n minus 1 change its position and orientation. Okay, so the angle alpha required for this match is 90 degrees, positive 90 degrees. Okay. Then unlike also of theta, alpha doesn't need to be added to a given joint variable. Okay, only theta can be added to a joint variable theta. Okay, so this is theta and alpha. So for further details of how to use this in a mechanical manipulator, so I will explain it later. Okay, next is the parameter D and parameter R. So the parameter D and parameter R are the position or translation parameters. So let's have an example here. Okay, so D is the distance from the origin of n minus 1 end frames along the z sub n minus 1 direction with joint variable if joint is prismatic. Okay, so D is the distance between two origins of the two frame. Okay? Of frame n minus 1 and frame n. Okay. So the distance here is not this gray line. Okay, this gray line is a hypotenuse, but this is not how we obtain the distance of these two origins. We will obtain the distance using the axis of z sub n minus 1 for getting the d parameter. Okay, so this is wrong. This is not the distance. Okay, so the distance along z sub n minus 1 is also called d. Okay, oops. So it is indicated by the link lengths. Okay, the link lengths along z sub n minus 1. The link lengths along z sub n minus 1 will be the distance d, or the parameter d. So in this example, the d here is a sub 1. Okay, so this should be like this. Okay, so a sub 1 is the link length. It is d. Okay, so this is d because it is the distance of the two origin, but along the axis of zn minus 1. Okay, along the axis of zn minus 1. So it should be look like this. Okay, oops, let me use a small eraser. Okay, a broken line. So d is equals oops, becomes an eraser. So d is equals to a sub 1. Okay, if this is a prismatic joint, it means it has a joint variable d. Okay, let's say it is a d sub 1. Okay, the joint variable d is d sub 1. So d here is equals to a sub 1 plus d sub 1. Okay, so just like joint variable theta and parameter theta, joint variable d1 is different to parameter theta. Okay, they are different. This is a joint variable. This is a parameter. Okay, so don't be confused. Okay, so this is for d, while r is the distance from the origin, again from the origin of frame n and frame n minus 1 along the x sub n direction. Now, it's at the x sub n direction. Okay? It is at the x sub n direction. So again, it is not the hypotenuse. Don't be confused. So along x sub n direction, or along x sub n axis, if there is a link length, example, a link length A2, okay, the link length A2 will be R. So this is equals to R is equals to A2. Okay, if there is a link length A2, okay, that will be the R. Okay, so unlike D, if it is a prismatic joint, you will add D sub 1 or D sub 2, D sub 3. You will not add anything to an R. Okay, an R parameter. Just write what is the link length in the parameter R. Okay, so these are the 4 parameters of the D-H parametric table. So we will have an example here. For the next video, we will have an example here, and it is a Cartesian manipulator. Then after filling out this D-H parametric table, I will also continue the steps of Denavit-Hartenberg notation. So I will plug it in our homogeneous transformation matrix formula. Okay.